All right, so now we move on to lesson 21, orbits and satellites, and this is the third lesson within Unit C. Now, where orbits and satellites go is it's again this reclassification or this classification, more simplistically, of a given centripetal force. So, in the first couple lessons, primarily 19 and 20, we dealt with what if we classify centripetal force as the force of friction, as a tension force, like in the case of a ball on a string in a vertical problem, or even on the horizontal. We could consider it to be Fg, and Fg is where we didn't really touch too much on. We did introduce it in verticality in terms of there is always an Fg or a weight component involved in a ball on a string or any sort of verticality in UCM. But for the most part, when we talked about this centripetal force being classified specifically as Fg, I alluded to the fact that we're going to talk about this in orbits and satellites. So here we go. Here's one of our classifications for centripetal force. Now, right away, in previous lessons, we've learned about horizontal and vertical components, and we dealt with these things independently. And, this even came back to lesson 10 when we dealt with projectile motion. We broke things into an X component, a Y component, and we solved problems based on that. Now, in terms of orbits and satellites, not to overcomplicate it or not to bring it back too far, but technically within these problems, we could end up getting projectile motion, just like including even lesson 19 and lesson 20. There's elements to have projectile motion, but we've tried to keep it pretty straightforward moving forward. Now, here's what we want to discuss with orbits and satellites. Orbits and satellites introduce this idea is what if we have some sort of object moving around a larger mass, such as a planet, and this is going to create some sort of relationship between the needed speed to keep the object in orbit and the gravitational force of attraction, which we call Fg. Now, looking at this piece here right away in the notes, we looked at this, and at low speeds, horizontal projectiles, they typically fly, and they'll fly for some time, but then they'll crash back down to the ground. And as the speed of the horizontal projectile is increased, typically what happens is it just lands further and further away given that certain speed. So if I give an object 10 meters per second versus 35 meters per second, clearly those are going to result in some sort of overall difference in the overall projectile length and distance in that case. Now, because Earth is round, now this introduces a new property where we're going to have to bring it back to our ideas discussed in lesson 19 and 20, where if we have some sort of centripetal force or we have some sort of curvature in the situation, then there has to be this relationship between whatever the speed of the object is and the given Fg, or that force of attraction between the two objects. Now, one thing to note right away is that all objects that are at some sort of projectile, or just like in lesson 10 or in this lesson, all projectiles typically are in this state of constant free fall, meaning they're going to want to be pulled down to the surface of Earth. But we propose this idea that what if we're able to, rather than put it with enough speed that will just come back down to Earth, what if we can force this thing to become some sort of satellite or join some sort of orbit at a given speed? And this is going to become very important. So in the example off to the side here, and in the video I'm going to link in the description, they break apart this description of what if we have this cannonball that's put, or this cannon that's right on top of a hill of some kind, and this looks pretty high off the surface of Earth. And they say, what if we take this cannonball or cannon and we fire a bunch of cannonballs at different speeds? Well, in order to get this thing into orbit, we have to find what is that perfect speed that puts this thing into orbit without it being gravitationally attracted back down to the surface and pulled and then landing at the surface. So we have all these speeds. We have speed here, speed here, speed here. These are all different speeds of cannonballs being shot from this cannon on top of this hill, but it's not until that the cannon can shoot a cannonball at the perfect speed does it stay in this orbit or maintain this perfect circular shape of this object in orbit around the larger mass. And the reason is, just point blank, before we go into more of this detail, is when you fire a cannonball out of this cannon, you're giving it some sort of tangential speed. So I'm going to call this V1. Now, if we give this enough tangential speed, rather than it being like a less than 10 projectile motion problem, it's going to have this where we have some sort of speed, which is that tangent speed. We have some sort of overall FC, and I'm going to use a straight line just to represent it, just like we've done before. This is going to be our straight line FG, or force of attraction between the objects. And in this unit, namely unit C, we're talking about uniform circular motion. It's the centripetal force bringing this in. And what these two cause is they have some sort of 90-degree angle here. So these things are perpendicular to one another. The force and the velocity are perpendicular to one another. And if we're able to fire this at the perfect speed, or if we're able to give it enough velocity, what's going to happen is that this force of attraction will only change the direction of the velocity, but not the overall magnitude, meaning it's not going to come crashing back down to the surface. Rather, if I was to draw another tangential velocity, if this thing was given enough speed, this could also be considered the same velocity, just on a different point in the orbit. And what we would notice is that, again, this is 90 degrees, and FC would equal to FG. The only thing that this force, centripetal force, or this force of gravitational attraction between the object in orbit and the Earth are doing is it's just changing the direction of that velocity. So there's this constant, almost like shift. And remember, this is how we define accelerated motion. Accelerated motion is a net force that can either change the magnitude and direction of a speed, or it can just change the direction of the speed. So for both of these, if you really wanted to, and here's what I would do in your notes, I would put a dotted arrow going down towards the middle of the Earth and say that that's the direction of the acceleration. And again, you could do that same thing on a second magnitude here. You could say, or a second vector arrow, you could say that the acceleration is towards the center. And we actually proved this back in lesson 19 and 20, where we said that change in velocity, or that change in tangential velocity on the outside, is what's eventually steering this change in velocity towards the center of the circle, meaning the acceleration is going towards the center of the circle. More simplistically, how I would think about this is if the overall FC, which we know from our previous lessons is actually equal to F net, if the F net is that centripetal force and it's going towards the center of the larger mass, we can consider this to be the direction of the acceleration. And again, that's just by definition of a F net, or a net force. Wherever the net force is, that's where the object is accelerating. Okay. Now, continuing on to our next page, we're going to introduce two different definitions here. Starting off, first and foremost, when we want to figure out the satellite speed, or the speed of the object in orbit, here's how we're going to do this. When we look at this, the gravitational force would act as the centripetal force for the circular orbit. So just as previously defined on the previous page, we can look at this and say that centripetal force, or that center-seeking force that we're looking at, is the FG, or the gravitational force of attraction. And so when we look at this, we can do the following off our formula sheet. We know this Fg is equal to the gravitational constant times mass 1, mass 2 over radius squared. Now, that's a given value, but what we're not given is this Fc. So a lot of you may look at this and be like, how come Fc equals this? Well, let's pull it apart. What we're going to do off to the side is say Fc is equal to MAC, because it's always mass times the centripetal acceleration. And then from this, we need to look at these two and compare them. And we need to be like, okay, so we have an M on both sides, or we have an M between both of these terms. So that seems fair enough. But then that should key indicate that our velocity squared over our radius is equal to that AC. And that is given to you on your formula sheet. So although this piece, the M times V squared over R, is not directly given on your formula sheet, what you are given is that your F net equals mass times acceleration. And in this case, we got to pick which acceleration we're dealing with. In the case of solving for speed, we need to pick this variant of the AC so that we can solve these problems. Now from here, what you notice is that you can cancel out the small mass. This small mass is the mass of the satellite. And so I can't emphasize this enough. Even I'm going to underline this in red here. The mass of the satellite is that piece we canceled out in red. And what this is saying is that if I can cancel out the mass of the satellite and progress forward to eventually isolate for V, and I get velocity of this satellite is equal to the square root of g times the mass of that larger planet over the radius between those two objects, what this is telling me is that regardless of the mass of that satellite, or whatever's in orbit, it's not going to affect the overall velocity needed to keep that object in the orbit. So I could take something like a pencil versus a 10 kilogram weight. Both of those two things would require the same velocity in their tangential velocity in order to stay in that orbit. So this is one way to view these problems. So if you're ever asked for speed, or you're given information about speed and asked to solve for something like a mass or a radius, you need to use this variant, or this definition. And what you could do is just kind of take a mental screenshot of this and be like, okay, when I'm solving for the speed of some sort of tangential velocity of an object in orbit, it has to be solved using this. But if it was a written response, most of the time I'm going to get you to derive this so you can actually show me where you're getting this speed from. Okay, now Flipping over our page to this piece here, this is where we just change our thought process just a little bit. So I'll highlight it with a different color. Rather than solving for the speed of an object, what if they asked us instead to solve for the period of orbit? Meaning, how long does one full rotation take? So I may even just write that, unless it's within here. When this question is under considering asking for the period, one should look for the centripetal force with the equation that has the period. Yeah, they don't give it to us in that nice language that we like. So period of orbit, I'm just gonna like kind of put a squiggle under this, arrow off to the side here, and say the period of the orbit is the time required for one complete rotation. There we go. Just to keep it simple for us, because as we move into the next unit, Unit D, and we start talking about the periods of a wave and periods of that in that type of context, it's very similar in definition. We just need to make sure that it's for one complete rotation or one complete cycle, just to have that language in our head here. Now, again, all we're going to do is if instead we're solving for the time required to complete one complete rotation, or we're trying to solve for the speed, it just means a subtle shift in our thought process when it comes to the formula here. So again, our classification of the centripetal center-seeking force is the force due to gravity, or that gravitational force of attraction, Fg. On our formula sheet, we are given this Fg, which is equal to g mm over r squared. Again, no surprise. Where we do need to derive, though, is this Fc, which is equal to this 4 pi squared mr over t squared. I don't like the way this is personally written. Some formula sheets include this, but our formula sheet doesn't. So again, what we're going to have to do is we're going to have to break this apart. I want you to write first and foremost off to the side, Fc is equal to, and now we know it's going to be mass times the centripetal acceleration, but now out of this equation, what I'm going to do is just rewrite it a little different. I'm going to write this as mass multiplied by 4 pi squared r divided by t squared. Now, hopefully, by taking this mass and moving it out front of the term, this is exposing what part is the AC. In fact, when I circle it on here, I'm going to do it on this one. So this right here, and I'm going to just try to put these things together, leaving out the m. The 4 pi squared r over t squared, which is also shown over on our derived part here, this is equal to the AC. And so we have this little mass that's in there, the mass of the satellite, but when you intertwine it with this actual formula, sometimes it's less obvious to see. So I like to just put it out in front as almost like the coefficient term. Now, what we can do with this is we can cancel the mass here, the mass here. Again, what does this say? That the mass of the satellite cancels, therefore, any object that would be placed in this given radius of the circle would require this amount of time to go. So regardless of which mass I look at, it's going to require that certain amount of time. Now, where this takes us is this derives us this formula here. T squared is equal to 4 pi squared over the gravitational constant mass of the planet times the radius cubed. And in fact, what this steers us into is Kepler's third law. And so we'll talk about this on the next page here, but I would recommend highlighting it on this page, and we're going to create some sort of proportional statement based on this that goes into Kepler's third law. Kepler's third law is this nice thing that is called the law of harmonies, and it basically relates all objects that go around a mass. So for all planets that go around the mass of the sun, or all objects that go around the sun, they would share this value called the Kepler's constant, and that Kepler's constant allows you to solve lots of unique problems here in terms of what is the radius of a planet, or what is the radius of the orbit, what is the period of that orbit if it's unknown given a certain information. We'll see an example like that. The proportional statement I want you to write based on this equation is that t squared is proportional to r cubed, or the period a planet takes to go around some sort of object squared is proportional to the radius of that from center to center cubed. Now, will we do lots of math with this? Not really, no. Where I would expect to see this is like later down the road when you're talking about like things in university where you may prove this idea, or maybe you take a class on like astrophysicists or astrophysics and you're taking these things and expanding upon them. For our case, we're not going to do too much work with them, but we will do a little bit of work with this Kepler's third law. So you want to be able to do that, which we'll show in the examples. All right, now flipping over to this section here, Kepler's laws of planetary motion. Now, again, we've covered these back in Unit B. In fact, we actually went over these, and when we look at the overall premise of this physics, the big note thing that we want to make here is the three laws that Kepler came up with. These provided the foundational knowledge for then Newton to take and derive and create mathematical statements that could give us the how this happens or give us the actual numbers that produce these values. But when we talk about the why or like is necessarily like what is happening within these planetary motions and how do we describe them overall, Kepler or Jonas Kepler is the one that produces that foundation. Now, let's just go through the three laws, very like surface level, and we'll just again remind ourselves of them. Planets orbit the sun in elliptical orbits with the sun at one focus of the ellipse. Meaning, if we look at our diagram on the right, let's suppose that this is the sun right here, this cluster. Well, that's one foci. When we look at both focuses together, the other focus would be right here on this ellipse. So one of those focuses, we have the ellipse being centered around that foci because we're considering it to be the sun. The other foci we're not going to pay that much attention to, but just know that an ellipse has these two foci. Rather than just, if it's a perfect circle, it would only have the one center point right here. Okay, that's the first one. So Kepler says, hey, objects are moving around in an ellipse shape. They're not these perfect circles like early philosophers and diagrams has shown and provided. The second one, a straight line joining the sun to a planet sweeps out equal areas in equal time. Essentially what this boils down to is if we look at our diagram, it's the law of sweeping areas. And it sounds super complex, but it's really not. If this is going to be area 1 between P and A, and this sweeps out over some sort of time, let's call it T. Well, what would happen is that if I considered maybe over here, as this is the area 2 between C and D, in the same time period T, A1 and A2 would be equal to each other. So we could make this assumption that the sweeping areas within a certain time interval are the same, or the areas are the same for a given time interval, no matter where it is on that ellipse. And so you would draw out two lines from that center or from that foci, which is the sun, out to the radius of the circle, or I should say the circumference of the circle. And from the center of the sun to the circumference of the circle, aka to the center of that planet, it would sweep out equal areas in equal time. And I know it kind of looks a little distorted because you're like, oh, A1 and A2, they look kind of different because one's like a thicker slice, one's a thinner slice. How could these two things be equal? But you got to remember, as you're looking in close here, you have some sort of wider piece of the circumference, but less actual height or less height to this object. Whereas on the other case, it's, yeah, definitely not much width or not much circumference, but a lot of height. So it's kind of a trade off between the height and the amount of circumference covered or how much it goes. And this relates to speed as well. Out in this region, I'm going to highlight here, in these Kepler, if you want to call them the Kepler observations, what you would notice is the speed out here would be quite slow. This object would be traveling at some sort of slower velocity, even though relatively it might be still very quick. It would be slower because when you go further away from the center of mass of that larger mass, the gravitational force of attraction decreases. So as this radius is larger than the radius, which is right here, what you would expect is that the gravitational force of attraction, or the FG here, would be less than the force of attraction which has existed over here with the shorter radius, because the closer you bring objects together, the more exponentially great their force of attraction is. As you're over here on this far side, it exponentially decays and you get that less gravitational force of attraction, and the field or the gravitational field that this sun would exert would be less on an object out here than it would be right here. Okay, so that's second law. Now, the most important one is this one here, Kepler's third law. The cube of a planet's mean radius, mean meaning average, if we need to make sure we have this, and I'll even highlight this in the notes, this is implementing the average. And I'm sure lots of you have heard of this at this point, being the average. The cube of a planet's average distance, measured as r, from the sun is proportional to the square of the period of a revolution t of a planet. So we get this nice identity in which we call Kepler's third law, and it's Kepler's constant, which is derived as the r cubed over t squared. Now, one thing we really want to note here, and I'll even just write this in here because I know it pops up a little bit here. We're going to write this as Kepler's constant. Now, hold on to this identity here because we will be using this in one of our practice problems. Okay, a couple things to note right here, right at the very bottom. Kepler gave no explanation as to why the planets go around the sun. Namely, his laws are only descriptive or observational. It wasn't until Isaac Newton came along that we get this why. So rather than just the how or the observational data, now we're getting the why. We're actually getting the math behind this. And Isaac Newton is the one that says, hey, I can tell you how these things are behaving or why these things are behaving using math. And the relationships I derive are going to be enough to tell us about the gravitational force of attraction and the field strength and all that other good stuff. So when we look at this piece here, now under this idea of Newton's why or his mathematical reasoning, we can then say, what is that mathematical reasoning that enables us to understand why planets are at the certain ranges they are, and what that means for their overall tangential velocity, what that means for their gravitational force of attraction, and what that means for the field and the field strength exerted on certain objects at certain radiuses. All right. Now, again, they do a Kepler's constant example for the sun, and we get a specific value of this piece here. And so this would refer to Kepler's third law, where namely that K value is here. And this can be derived using our Fc equals Fg, where we use our period, we use our radius. We do a bit of algebra to lift up the radius over to the other side, the period over here, or keep the period here actually. And then we just isolate for this and find that this G or GM, which is the gravitational constant times the mass of the larger object, in this case, let's consider it to be the sun, over 4 pi squared equals this K value. Because this piece, the only thing we'd be substituting from one problem to the next is the mass of the given larger planet. And so in most cases, what we like to do is we like to consider this larger mass to be the sun. And then for all objects that go around the sun, like Earth, Mars, Mercury, all these other things, we're going to make sure that they have some sort of ratio that can be equal to the ratio that would be given by the sun. And we call this Kepler's third law, law of harmonies. Okay, let's do some practice problems here. So in the practice problems, again, when we're doing these practice problems, we really want to think about these in terms of we're classifying a force, or we're classifying that centripetal force, that center-seeking force, as the gravitational force of attraction. What is the speed required to put an object in orbit that is just above the Earth's surface? So when they say just above, let's mean that it's actually just going to be the Earth's radius, because we're just going to apply it like millimeters from the Earth's surface. Now, that's a bit of a broad generalization because the Earth's surface isn't completely flat, but we're just going to assume that the radius is the average radius, so it accounts for like mountain range and valleys, so the peaks and valleys are included there. What is the speed required to place it just above the surface? Here's the math. So we're going to say we have Fc, which is equal to Fg. First and foremost, we want to make sure we classify our centripetal force. Now I'm going to expand this out to be mass times the centripetal acceleration is equal to, based on our formula, as soon as we know it's planets moving around each other or anything planetary, we want to make sure we're saying g mm over r squared, where this is on our formula sheet. Now, what I recommended in class is when we got to this step here, I definitely said that you should just cancel out the small mass or the mass of that object that's orbiting the larger object, in this case, the Earth, because the satellite or that orbit isn't going to have much impact on our overall situation. Now, we have to choose an AC from our formula sheet. AC can appear in two different forms, one involving speed, one involving period. Because they told us to look for the speed, or they said, what is the speed required? We're going to make this v squared divided by r is equal to g capital M divided by radius squared. Now, continuing this up here, I'm going to cross multiply this. So I'm going to take the r and I'm going to cross multiply it from the denominator here up to the numerator. And when I do that, my statement becomes v squared, which is equal to g m multiplied by r divided by radius squared. Now, using our 10c skills, we would cancel out one of the r's from the numerator, one of the r's from the denominator, and this is going to give us v squared, which is equal to the gravitational constant times the mass of Earth over the radius of Earth. Lastly, we're going to say v is equal to the square root of g m over r. Perfect. Now, that's that general formula we derived a couple pages ago of what is the speed of an object required to keep the object in orbit. Okay, now we're going to plug in all the numbers here and we're going to get a specific value. So I'm going to continue this up here and say that the speed or the velocity is the square root of, now we want to make sure all our units are here, so I'm going to go 6.67 times 10 to the power of negative 11. This is going to be newtons times meters squared divided by kg squared. Again, this constant is on the back of your formula sheet. I'm going to include that all in brackets. I'm going to multiply the mass of Earth, which is 5.97, times 10 to the power of 24, and this is kilograms. There we go. And now I'm going to divide this all by the radius of Earth, which is 6.37 times 10 to the power of 6 meters in brackets. There we go. Now, what I'm going to find is that the speed is equal to 7.91 times 10 to the power of 3 meters per second. And this is to keep that object in orbit at that given range. So if an object is just above the Earth's surface, it needs to be going roughly about 7,000 meters per second, which seems very quick, but in order to overcome the gravitational attraction of FG that is trying to pull it back down to the Earth's surface, it does have to be going really quickly. And one thing, if you watch the video that I'm going to put in the description, which I highly recommend you do, as objects are closer to the surface of Earth, the atmospheric density is increased. So you get more impedance to the motion or more resistance to the motion of the object. There's more interactions between the object orbiting and the overall particles in the air. And so therefore there's that frictional resistance there that slows the object down. As it slows it down, it's going to want to then continue to pull this thing back down to Earth. It's kind of a double whammy, which is exactly what they say in the video. So in order for this object to be going just above Earth's surface, it has to be going extremely quickly. And the realism of this being maintained is quite low because, again, there's going to be that atmospheric drag, as it's called, which is going to then want to slow the object down or impede its motion. And therefore, it may succumb to that overall decrease in speed and just crash back down to Earth. Okay, next problem here. The space shuttle orbits the Earth at an average of an altitude of 500 kilometers. What is the period of the orbit? Okay, so they're asking us something slightly different. First and foremost, we want the period or the t value, and they give us this average altitude, which it exerts or which it is at, where it's located. What we need to do is right away, just like I've been telling you the whole year, they love to see if you'll get caught on this on the final exam or on any sort of exam. So what we're going to do, right away, we're going to deal with the kilometers. The average altitude, I'm just going to call this like radius A, because this is how far it is above Earth's surface, is equal to 500,000 meters. We're going to multiply it by 1,000, and that's going to give us that new value in meters. Now that we have this new RA, or this value that it's above, what I'm going to do is I'm just going to zoom out here, and we're going to start the problem. Again, we're starting off with FC is equal to FG because we want to classify our centripetal force. This is going to become mass times the centripetal acceleration, which is equal to capital G m over r squared. I'm intentionally making that little m, or that second m, small. Now what we can do is, to simplify our job, cancel out the mass of that object that's in orbit, because again, it's not going to have significant impact. In fact, all objects at this altitude would need a certain speed or have a certain period. Then what we're going to do is we're going to classify our AC, because on your formula sheet you have two of them. We're not going to use the speed. And this time we're going to use the one that involves period, which is equal to 4 pi squared multiplied by the radius divided by t squared. And this is equal to g m over r squared. Now, our goal is to solve for the period, or we want to solve for t. So I'm going to cross multiply this. And I highly recommend you do that same thing. Multiply this, multiply this. Okay, continuing that next step, we're going to get everything where it's in the numerator on the next line. So this is going to be 4 pi squared multiplied by, if you notice, we have r times r squared, that's r cubed. So I'm going to make this r cubed. And then this is going to be equal to, on our other side, we have t squared times gmm, or gm is multiplied by t squared. I guess I should write it like this. Now what I'm going to do is divide both sides by the gm, or the gravitational constant, and the mass of Earth. And then this is going to give us t squared, which is equal to 4 pi squared radius cubed. Whoop, that 3 is a little off. There we go. Divided by gm. Very last thing to do is square root both sides. So I'm going to take the square root of both sides, and therefore my period that I'm looking for is equal to the square root of everything under the blue square root. Let's just make sure we put it all here, and then we'll put it together a final answer. So in your calculator, please do not put, even in your algebra, don't write pi as 3.14. It has a lot more digits than that. In fact, it's an irrational number, so keep it as pi, because I know your calculators are smart. 4 pi squared multiplied by the radius cubed. We got to be very careful with this one. This is where we got to look back to our beginning part of the problem, and we said that it exists at an average altitude of 500,000 meters above the Earth, or 500 kilometers. So what we need to do is we need to add the Earth's radius and that altitude, because it's center to center, or from the center of the Earth to to the center of that satellite. So I'm going to first and foremost write 500,000 meters, then plus 6.37 times 10 to the power of, I believe this one is going to be 6 meters, and then it's all cubed on the very outside. Now, we want to divide this by our GM. So our G is equal to 6.67 times 10 to the power of negative 11 multiplied by, and I apologize, I'm not going to put units for this gravitational constant. You need to do that on your test or any sort of assessment, but I'm not going to put it there just because it's really close with the work from the next problem. Now, I'm going to multiply this by 5.97, which is the Earth's mass, times 10 to the 24 kilograms, and I'm going to put that in brackets here. Okay, now we go up here and we're going to put in that our t, or the period, is equal to, and then based on this, we're going to get that is equal to 5.67 times 10 to the power of 3 seconds. And so I'll just arrow up there. I may even have enough room down here. So what I'm going to do is I'm just going to shift this down here. I didn't realize I had enough space here. I'm going to shift it there, highlight it, and just put an arrow indicating that that's where our work tended to go. Now, what this means is that it took 5.67 times 10 to the 3, or 5,670 seconds to do this full rotation, or one complete rotation at that altitude around Earth. What I'm going to do is I'm just going to look at this and be like, okay, well, actually, maybe I'll just leave this as a challenge for you, because I know in the period they like to leave it as seconds. I was going to say I could do a simple calculation here just to see what this would be in terms of hours, but I'm going to leave it at this for you. You could convert this into hours, days. They may even ask you to do that. But for the most case, we always treat period in terms of how many seconds does it take. And so I'll leave that challenge up for you to do. Okay, now number 3, the average distance from the sun to the earth is 1.49 times 10 to the 11 meters. What is the mass of the sun? And then they first of all ask us this hint here, and they say, how long does the earth take to orbit the sun once? And the reason they ask us that is because we need the period value in order to figure out what is this overall mass of the sun. So it's really important because they gave us a radius or a mean radius. They ask us for that mass, but now we're just missing that piece where we need to figure out, okay, what is that period before we can progress? And you'll see why we need the period when we establish our equation. So how we're going to get this thing here is typically in most questions, they would give you the information within the problem, or they would give you a little sub bubble to look at to get the information. For us, the hint of how long does it take the Earth to orbit the sun, we're just going to figure out this information from our table here. So I'm going to skip forward here. And first and foremost, I'm going to go to the Earth tab, and then I'm going to scan all the way across. And this is going to be the value we're looking for. When they say the period of revolution of the orbit, it's referring to how long does this take to go around the sun one time. Now, for some of you out there, you're probably like, oh, we could just manually calculate that because it's technically 1 year. How much time does it take to go around the sun once? But if you were given that value like we are here, we're just going to copy it, 3.16 times 10 to the 7. Okay, so I go back here. I'm going to write that just up right above here. T is equal to 3.16 times 10 to the power of 7 seconds. There we go. Okay, now we're going to begin the problem here. Again, we always want to start with our Fc equals Fg because it's referring to gravitational attraction of two objects. This is going to make me have mass times the centripetal acceleration is equal to Fg, which is equal to capital G, large M, small m, divided by radius squared. And then what I'm going to do from here is this small mass, or the centripetal mass, refers to the mass of the Earth. So I want to cancel that out from both sides because the mass of the Earth isn't going to impact what it looks like to have the mass of the sun, obviously. So any object that has this certain radius and this certain period should, in fact, have this sort of mass that is controlling it or controlling that orbit. So we cancel those out. Okay, now we go AC. AC can have the two different forms, but in fact, because they said in the hint, how long does Earth take to orbit the sun, and we have that value, it means we have our t value. I'm going to write this as 4 pi squared multiplied by r divided by t squared, and this is going to be equal to gm over r squared. Now, the value we're looking for here is m, or the capital M. So to get rid of the two variables that are attached to it, first and foremost, let's multiply up our r, and then we're going to divide by our g. But let's just do these in separate steps because I want to make sure that we can track all of the information going here. So this is going to be 4 pi squared. R times r squared, just like before in the previous problems that we've done, is r cubed divided by t squared. Now, what we're going to do here is say this is equal to g m, and we're going to divide both sides by the g, or the gravitational constant, which means it will join the t squared down in the denominator. So then we get mass of the sun is equal to 4 pi squared r cubed, or the mean radius, and I'm going to make sure my threes are good. I know sometimes they look a little off, t squared multiplied by g. Now, the t squared and the g can be in either order. You can have one before the other. It doesn't really matter because they're being multiplied. So if I change the order, apologies there. Now, one thing I'm going to note just before I start plugging in the numbers is, if this helps you, sometimes what I do, and this is what I used to do in math, I would label the variables. So if this is mass of the Earth, just put ME. And then if you know the small mass is the mass of the Earth, just put ME there. If we're talking about the mass of the sun, put an S here. Just put an S all the way through the problem here, indicating that this is the mass of the sun. If that helps you solve these problems and recognize like what mass is what, I would just put subscripts. It's a good way to keep track of your information, easy way to kind of solve these problems. Now, we're going to write this in as mass of the sun is equal to 4 pi squared. Radius, they gave us that radius, which was 1.49 times 10 to the 11 meters. And this is going to be cubed, so I'm going to write it to the power 3. We're going to divide it by the t squared, which we found to be was 3.16 times 10 to the power of 7 seconds. So very, very large amount of seconds, times the gravitational constant, 6.67, times 10 to the power of negative 11. And now, because I have enough space, I'm going to try and force this to have the units in here. This is newtons times meters squared over kilograms squared. There we go. And then therefore, let's see if I have enough space here off to the side. I do. I'm going to write this in as mass of the sun is equal to, and the nice thing is we have those answers in the bubbles here. We get 1.97 times 10 to the 30. 97 times 10 to the 30. And this is in kilograms. Now, for some of you, you may have gotten 1.96 times 10 to the 30. And the simple explanation boils down to this. Because we're using simplified, truncated, and by truncated, I just mean like shortened form of the actual radiuses and the masses and the amount of seconds, this is going to be a value that isn't fully accurate. And what would happen is, if you moved on to the post-secondary level, or you were doing any sort of like official measurements in whatever career you're in, most of the time you're going to use a calculator that is advanced enough to hold on to the entire number and use the entire number in the calculation. So if you're an accountant, you wouldn't just be like, oh, I have $1 million in this account, and this account is therefore I'm just going to use $1 million and that's it. The account might have $1,100,007. That's a totally different value than just a million. So you need to be careful with this in the case of, in grade 11 and in grade 12, sometimes we just truncate these values and we just simplify them for numeric sake. But in reality, if you had a computer and you were doing all these calculations and able to pull this information, the number might come out a little different. So I will caution and say some of the masses might end up being like 1.96 times 10 to the 30. Some of them might be 1.97. You're going to notice that there is some sort of fluctuation in these. So if you get anything a little different, now what wouldn't be acceptable is if you got an answer like, oh, mass of the sun is equal to, and I'll just write this in here, equal to like 3.00 times 10 to the 30. Now that's way off. We don't want a value like this. This would be like, I'd give you no marks right there because that's not fair. But if it's within that hundredth, then you're kind of implying that, there is room for fluctuation with the fact that these values are not exact values, rather they're truncated, more simplified values. Okay, now moving on to our last two examples. There was originally another example 4 here that was a little bit different, so we'll get to that in a second, but for now we're going to look at this problem. It wasn't in the original notes, it's more of a bonus problem, but it's included in these notes, which I really like, and it kind of introduces a topic that is a little bit interesting for us, so we'll use it for our sake. Okay, here's the problem. A geosynchronous orbit is where a satellite maintains the same position above a certain point on Earth's surface for any given unit of time. At what height above the Earth's surface must a satellite be positioned in order to have this geosynchronous orbit? Now again, just by pure definition, a geosynchronous orbit refers to the following, and I'll even just draw it off to the side just so we have like a rough understanding of this. Suppose that's Earth's surface, which is this black curvature, and then there's some sort of satellite that sits X distance above. We don't really know the radius, but that's what we're trying to figure out. They're claiming that no matter where this satellite is in its trajectory, and I'm going to just draw in 3 spots here, and then I'm even going to draw a dotted line that represents the trajectory of this orbit. There we go. They're claiming that if I'm a person that's here, I'm a person that's here, and I'm a person that's here, and this is us rotating. Maybe we're rotating in the clockwise direction. Well, what they're claiming is that the position of the satellite will match the person at each key point or each key interval of time. And so it stays exactly stationary to the observer, but technically both objects, whether it be the person or the satellite, are rotating together. So that's what this is saying. Now, how we solve this is first and foremost, we got to think about it in terms of what is the period of an object that's on Earth, or what is the time it takes for an object to complete one full rotation on Earth. And if we actually did the numbers here in a given day, which is 24 hours, 24 hours, if we take, and maybe I'll write this down just to make sure we're actually tracking this, the period on Earth is equal to 24 hours, but because our calculations don't involve hours and we want seconds, you would do the conversion from 24 hours into seconds, aka we're going to take this number and multiply it by 3600, which is the seconds in an hour. So 3600 seconds. And this is going to give us a value of, in one day, which is 24 hours, we get 86,400 seconds. So this is that period value for one complete rotation of not only the satellite or this geosynchronous orbit, but it's actually a person on Earth too. So I guess I could just classify it as this is the period of a geosynchronous orbit for a person on Earth versus a satellite that is rotating at some sort of distance. Now, what we're going to do is we're going to set up a statement where we figure this piece out here in the following way. Again, the question is going to be set up very similar. Fc is equal to Fg. We always want to classify our centripetal force given the situation. In the case of orbits and satellites, it will always be Fg. Now we're going to go mass times the acceleration, or the centripetal acceleration, is equal to g m over r squared. Again, the rate or the mass of the given smaller object, in this case the satellite, is non-important to us. It doesn't have any relevancy for the rest of our calculations. So we're just going to cancel it. What we want to figure out is, because we were given enough information, or we knew enough information for t, we're going to use the AC that involves 4 pi squared multiplied by r divided by period squared. Now I'm just going to tidy that up a little bit. There we go. And this is equal to g, mass of the Earth, over radius squared. Now what we're trying to solve for is the radius, so let's just do a little bit of algebraic work with this. So I'm going to cross multiply. This is going to become 4 pi squared r cubed, because I multiply the r and the r squared together. This is going to be equal to, on the other side, t squared multiplied by g m. And then what I'm going to do is I'm going to divide both sides by 4 pi squared. Dividing both sides by 4 pi squared, I get radius cubed. Oh, my threes are always bad. I know it. Don't gotta tell me twice. There we go. Radius cubed is equal to t squared times g m over 4 pi squared. And then from here, we're just going to cube root both sides. So I'm going to cube root the left, cube root the right, and therefore my radius, or the total radius center to center from the middle of Earth to the middle of the satellite, is equal to this value of the cube root of, and now we're going to plug in all these values here. So first and foremost, the period is equal to 86.4 squared, or seconds squared, multiplied by the gravitational constant, 6.67 times 10 to the power of negative 11. This is newtons times meters squared, divided by kilograms squared, multiplied by the mass of Earth. So this is going to be 5.97 times 10 to the 24, and this is in kg. And then I just got to extend my cube root here, divided by, in the denominator, again, don't simplify that value, 4 pi squared. We don't want to put in like 3.14 squared. Make sure you put in the full irrational number of pi, because your calculators are smart. Now, the number one thing we're going to notice is that our radius based on this value is going to give us the following. R is equal to, and I believe according to my calculations, we get 4.22 times 10 to the power of 7 meters. Now, what we need to classify and what we need to annotate is that this is the total radius. This is that radius where we not only include the altitude, or how far it is above the Earth's surface, but we include from the center of Earth to the center of that. That's not what they asked for. They said at what a height above the surface of Earth. And that might be an important thing to go back and highlight, just so we're really sure of our answer. Where should it be positioned in order to have this geosynchronous orbit above the Earth's surface. So if this is the total radius, then we're just going to do a really simple calculation to end this. Here's what we're going to do. Right above our little diagram here, we can say, therefore, the radius above, or the radius A, if we want to call it that, and even in our diagram, we could write this in here. The radius A that we're looking for is equal to the radius total minus the radius of the Earth. Now, mathematically, what this is going to give us is the radius we just figured out, which is 4.22 times 10 to the power of 7 meters, minus the Earth's radius, which is 6.37 times 10 to the power of 6. And therefore, the radius above, or our RA, is equal to 3.59 times 10 to the power of 7 meters. Excellent. There we go. So we're going to highlight this value here. And maybe what I'll do is just like arrow up over to here saying that like we continued the problem over here to simplify this. Now, it's definitely not the neatest work, but I'm hoping that you understand that when we calculate the radius, if we don't do any sort of algebraic step within our actual calculation, we're actually calculating for the total radius from the center of Earth all the way out to the object. That would be that radius we found. But we're more interested in how far directly above the surface of the Earth. Easy calculation, just subtract away that radius of the Earth here. Now, our diagram doesn't really do it justice because it's a very large distance away. 3.59 times 10 to the 7. In fact, that's actually larger than the radius of the Earth. So the object would like realistically be way, way out here, somewhere far off the surface there. And this would result in that geosynchronous orbit, like we said, where the person and the satellite would be uniform at any given unit of time. Okay, kind of an interesting one. Now, let's flip over to our last problem, which was the original number 4, and it's this one. And it gets us to kind of take the two approaches of Kepler and Newton and then break them apart in terms of how can we solve problems, or how can we solve for information using Kepler's third law, and then how can we use Newton's logic or Newtonian logic to help us solve this. Newtonian logic, just to put it really simply, is the math and the algebra we've just been doing. So in those first 4 questions, we use Newtonian logic. Kepler's third law logic is going to involve the Kepler constant for objects moving around the sun. So here's the situation. If Earth's orbital radius from the sun is 1.49 times 10 to the 11, and the period of that revolution around the sun is 3.16 times 10 to the 7, both of them would be given to you. Calculate the period of revolution of the planet of Venus, whose orbital radius around the sun is 1.08 times 10 to the 11. The sun's mass is 1.98 times 10 to the 30. So again, even in this question, they're giving us a different value, which is kind of funny here. So, I mean, well, we're looking at this and seeing like what is the actual value here. But in this case, on the previous page, we looked at the sun's mass and got 1.97. Here, they're saying it's 1.98. So kind of getting conflicting statements here. Okay, now when we look at this piece here, let's do our setup here. So first and foremost, we want to figure out what is the period of revolution for Venus using Kepler's third law. So we're going to use the third law logic first and foremost, part A. It said that if I take the radius cubed for an object like Earth or a mass of Earth, and I divide it by the period squared of Earth, then this must be equal to the radius of Venus cubed divided by the period of Venus squared. And this goes back to Kepler's third law, which says that there's this law of harmonies. For every object that goes around the sun, they share this common radius, or they share this common value, which we call K, the Kepler's constant. So all objects that go around the sun have this Kepler's constant identity that they share. Now, what we're looking for is the TV, or the period of Venus around the sun. So we're going to have to do a little bit of cross multiplication here. Let's cross multiply both the denominators away. When we cross multiply both the denominators, we end up getting TV squared multiplied by radius of the Earth cubed is equal to period of the Earth squared multiplied by radius of Venus cubed. And I'm just going to clean up this one a little bit. Radius of Earth cubed. There we go. Now we're solving for that TV squared, so I'm going to divide both sides by the radius of Earth, or RE cubed. There we go, divided by RE cubed. Excellent. Now this is going to end up giving me TV squared is equal to TE squared times RV cubed divided by RE cubed. There we go. Now, this ends up giving me, when I square root both sides, because I want to make sure I have my TV, or my period of Venus around the sun, as an individual value, not a squared value, I'm going to end up getting that TV is equal to, now let's just plug in all the numbers, according to what they gave us in the above information. So the period of Earth around the sun, period of Earth around the sun is 3.16 times 10 to the 7. And this was seconds. This is going to be squared multiplied by the radius. Let's just go up here and get that value. 1.49 times 10 to the 11. And because it's a radius, we're going to cube it. And then in the denominator, we want the radius of Earth. Oh, I just got to make sure I put the radius of Earth in the denominator. So the 1.49, that needs to be placed in a different spot. Rather, I need to put the radius of Venus there. Radius of Venus is equal to 1.08 times 10 to the 11. So that should be the one in the numerator. 1.08 times 10 to the 11, and this is meters. And then in the denominator, that's where we're going to put this 1.49 times 10 to the power of 11 meters, and this will be cubed. Perfect. Now, we're going to calculate the period of Venus, and the period of Venus is equal to 1.95 times 10 to the power of 7 seconds. So this is how long in seconds it takes for Venus to orbit the sun one time. So here's our value. Now, what we want to do is we want to move on to the Newtonian logic, which is stuff that we're more familiar with from today. So one way of dealing with it is this nice Kepler's third law, or using part B, we're going to look at it using Newtonian logic. So part B, I'll do off to the side here. We're going to classify our centripetal force equal to Fg in this case. Now, from here, we're going to say mass times the centripetal acceleration is equal to capital G large M over small m divided by the radius squared. We're going to cancel the mass of Venus. Again, if you're one of those people that like subscripts, what I would do is just be like mass of Venus, mass of Venus. This is mass of the sun right here. Okay, we cancel the mass of Venus. The nice thing is we're given the period of the Venus around the sun. So we're going to use the variant, which is actually, oh yeah, because we don't have speed, we don't want to use the other one. So we're going to use this one, 4 pi squared multiplied by the radius divided by period squared, which is equal to g m over r squared. We're solving for t squared, or namely t, so I'm going to cross multiply this stuff across so that I can get rid of the t out of the denominator. This is going to give me the following. We have 4 pi squared multiplied by radius cubed, which is equal to g m multiplied by t squared. I'm going to divide both sides by the gm, or the gravitational constant times the mass of the sun. And therefore, when I look at this, I'm going to get t is equal to the square root. And now we got to square root all of this stuff. 4 pi squared radius cubed divided by gm. There we go. Now, we actually have to plug in all the values here, so we're going to do that below. T is equal to the square root of, and so I'm going to keep it as 4 pi squared because I don't want to make it 3.14. Again, we want to hold on to that value. The radius around the sun is equal to 1.08 times 10 to the 11, as given above and previously mentioned in the last problem. And then in the denominator, what we want to do is put in our 6.67 times 10 to the negative 11, which is the gravitational constant, with its units, newtons times meters squared over kilograms squared, multiplied by the mass of the sun. The mass of the sun is actually given to us right in the problem here. So again, on the previous section, we had 1.97 times 10 to the 30. In this one, we're just going to use that 1.98 times 10 to the power of 30, which may actually indeed be the more accurate calculation, but who knows? And then from here, we're going to get the value of 1.94 times 10 to the power of 7 seconds. Highlight that, great. This is our period for Venus as it goes around the sun. Now, here's what I want you to recognize, that whether we use Newtonian logic, which is part B, or we use Kepler logic or Kepler's ideas, Kepler's third law in particular, we end up getting the same value. Now, you're probably questioning this, just like my students did in class. Why is there a discrepancy between the two? We end up having two things that are supposed to equal the same value, but they end up different. How does that happen? Again, it goes into this logic that we had talked about previously in this lesson, where if this object and its numbers are all truncated. So in the examples here, we have 1.08, we have 149, 3.16, all these truncated values. Same with over here. This is going to lead to inaccuracies, because realistically, if I took like some sort of calculator, some sort of computer, and I took the actual values, the full values to all their decimal places, their entire number, what we would end up having is that these two sides would be completely equal to each other. But I mean, there is room for discrepancy here when we're using two different methods that not only have different numbers, but they have truncated numbers within them. So we need to be very careful with that, realizing that the two methods are going to give you approximately pretty much the same value, but unless we actually had all the values plugged in here, the entirety or the value in its entirety plugged in, it would be very hard to put these two side by side and get the exact same value. Now, for some cases, you might get the exact same value. For others, just depending on the math we're doing here and the numbers we're plugging in may be a little different. So not that we see Kepler's third law a ton, but in some of the practice problems and maybe even in some of the quiz problems or maybe some problems you see moving forward, you might be required to do one or two of these just to show that, hey, this common ratio is a nice way of solving it, and it gives a lot of power behind Kepler's third law, and it also allows us to compare to the Newtonian logic, which Newton took his ideas, or Newton took Kepler's ideas and then expanded them. So it's kind of nice to see these things go hand in hand, especially because we didn't really see directly how these things went hand in hand in our previous unit, but now we kind of get to see that nice tangent between the two of these. Okay, now here's where you want to go on to your practice problems. I recommend going through all the practice problems. There was a lot to this, and to fully master this, you're going to really want to make sure that you try out a bunch of these problems of how we classify the centripetal force as this force of attraction due to gravity, or this gravitational force of attraction. All right, good luck with your practice.